How are you doing, guys? I'm Baha, and here's lesson for part 1, which is about image segmentation. So these are outlines for today's video. So first of all, we are going to discuss what is image segmentation, and we are going to work with CAMVID dataset. Then we are going through transfer learning, and we are going to build our model. So we are going to use unit architecture, and the final part is about inference. So let's get started. Okay, so first let's look at image segmentation. So what exactly is image segmentation? Image segmentation is a process of partitioning a digital image into multiple segments. So you could call it a pixel-wise classification. So what that really means is on a pixel by pixel basis inside of our image, each pixel represents some class of some degree, whether it's background or cat or dog, and we can then try to classify and localize areas inside of images to explain where everything is. So it's like object localization. For instance, here we have some brain hemorrhage photos, and we try to segment this particular section, which shows signs of being health harm. So we train our model to segment these particular sections of the brain, as you can see here. And here's another example. So here we try to identify where is the plane in a picture, and the output is this, and we call it a mask. Okay, so for our problem, we are going to use Vision Library because it's a vision task. So here we import all from fastai.vision.all. And the dataset that we are going to use is called CAMVID, and it's a segmentation-based task where we try to identify from 32 to 36 different classes inside of various images, and all of them were taken from cameras on cars. And here we use UnterData method to grab the path of our images and store them into a path variable. Okay, so let's grab our validation set. So our validation set is inside a text document called valid.txt. So here we construct a path of the validation set, which is valid.txt within the extracted dataset folder. And read_txt method here is used to read the content of the file as a text. And the split_n is used to split the content into a list of file names, and these file names are then stored in valid if names variable as a list of strings. And here we show the first 5 elements from our valid if names list. And now let's look at an image and make sure that everything is looking okay. So here we make a path for our images and path for our labels. By using this way, we can get the file name through getImageFiles method. So here we pass the path of our images to getImageFiles and store them in ifnames variable. And we do the same for our labels and store them to LBL names variable. And now let's look at an image. So here we grab the image with index 10 and pass it to PIL_image.create. Then we show our image. So as you can see, it's a scene of a street. And the goal of our task is to identify where is the person, where is the traffic light, where is the buildings, the ground, the trees, and so on. Okay, so now let's grab our masks for these datasets. So they live inside a labels folder, and they have _p right after each of these file names. So here we create a lambda function that takes a file path object O as an input and return the corresponding path to the segmentation mask files for that input file path. So as you can see, the path variable here is a path to the root folder that extracted CAMVID dataset. Labels a subdirectory that contains the segmentation mask file, and O.stem and O.suffix are attributes of input file path object O that respectively represent the file name without the extension and the extension of the file. So this lambda function concatenates the path labels and a string that constructed using a file name without the extension and suffix underscore b to represent the segmentation mask file name. So the stem and suffix grab everything before and after the period respectively. And for our masks, they are of type PIN mask. So let's go through a quick example to make it clear for you. So let's say we have 8x8 image and where the zeros represent the background. So what the mask is going to do is in that particular block here, we say that one is a bird or dog. So now in the original image, which also an 8x8 image, at these positions we will identify them as a bird or dog. So now if we call show method, it will create a color schema for us that shows different colors for each of these different classes. So now we have a person in blue, ground in brown, and these signs in red, and so on. So our model is going to discern for each individual pixel. And for now, if we look at what our mask actually is, we can see it's a giant array of pixels. So here we print them, and as you can see, each of them has individual numbers for each of these classes, and each number from here has a code associated with it. So for this case, we have code.txt document that has what exactly each of them is. So if we load this document here and we print it, and as you can see, here's our codes. So now we need a split function that will split from our list of valid file names that we grabbed earlier. So let's try to make our own one. So here we define our file splitter function that takes file name as an input. And in this line of code here is going to read the content of our input file, then convert it to a list by using .split method, and store the resulting list in a valid variable. And here we define our inner function, which is underscore func, that takes file path object x as an input and check if the name of x is in valid list. If it is, it will return true. And here we define another inner function that takes object O and optional keyword arguments as an input, and uses func splitter to split the input object O based on the previous inner function, which is underscore func. So in summary, these takes in our file names and check for all of our file names in all of our items in our validation file names. So now let's go through to transfer learning, because one technique that we can use is called progressive resizing. So this technique helps us to gain more accuracy, and what that means that we started training on much smaller sized image, and as we get larger and larger, we will be able to get higher accuracy. So Jeremy popularized the idea of image resizing, so we start to train on smaller sized images. Eventually, we get larger and larger, then we define our transfer learning loop. So in the first round, we will train at half the image size. So here we check the shape of our mask, so it's 720 by 960. And here we are going to split it in a half, and as you can see here is the new size, which is 360 by 480. So now we are going to define our data blocks. So the blocks argument here specifies that the dataset consists of pairs of images and segmentation masks represented by image block and mask block respectively. And getItems argument here specifies the functions that will be used to get the list of files for the dataset. So here we set it to be getImageFiles. And for splitter argument here specifies the functions that will be used to split the dataset into training and validation sets. And here we set it to be file splitter functions that we defined earlier. And for getY argument here, this argument will specify the functions that will be used to get the segmentation masks. So here we set it to be getMask. And the batches transforms argument here specifies a list of data augmentation and normalization transformations that will be applied to the dataset during the training. Okay, so for this dataset, because segmentation takes a lot more memory to do, so we are going to use a batch size of 8. So here we call our data loaders, pass it our path, along with our batch size, which is 8. And for now, let's take a look at a batch. And here we show a batch with a maximum number of 4, and as you can see here that our segmentation mask is overlaid on top of the original image. So let's make our vocabulary, which is a part of our data loader. So with this dataset, we have a void color, and we don't want to use that void label when we are training. So here we set our vocab attribute to be equal to codes. And for now, we need a methodology for grabbing that particular code from our output of numbers. So let's make everything into a dictionary. So here we made this name2id, which is our new dictionary. And if we print it, so as you can see, the first key is animal with value of 0. And here we have a void key with value of 30. So now let's make our accuracy function. And here we set our void code variable to be equal to the value of our void key, which is 30 as we saw. And for segmentation, we want to sequence all the outputted values to have it as a matrix of digits for our segmentation mask. So from there, you can take the argmax of anything you want and check them between the input and the target, then take the overall average. So this function is going to do this. So first of all, we are going to sequence our target. Then we grab everything that doesn't include our void code. And then we check to see what the overall accuracy was for that. And now let's go to the model. So we are going to use unit. So unit allows us to look at pixel-wise representations of our images through sizing it down and then blowing it back up into a high-resolution image. So the first part we call it encoder and the second part we call it decoder. So let's take a look at its architecture. So as you can see, unit is a fully convolutional since it contains only convolutional layers and doesn't have any dense layers. So here we have our input image. So it's going to scale down and then we scale it back up. Here's more details. So as I told you, unit architecture is consist of 2 parts, the encoder and decoder. So let us start with the encoder part. So the encoder part tries to understand the what of the image. It does it by using convolutions and max pooling. So you can think of the architectures in terms of levels. So we have here level 1, level 2, and so on. And each level is consist of two 3x3 convolution layers followed by relo activation, and the transitions between each level is handled by 2x2 max polling unit with a stride of 2 for downsampling. So if we go down of this U shape here, the size of the input halves and the number of channels doubles. So as you can see, the input size in this level is 572, and in the next level is going to be 284, and number of channels here is 64, and here the number of channels is 128. So this is a downsampling process, and in the decoder part here it does upsampling, because our goal is to get an output that is similar in size to the input. So here we are going to upsample the condensed information in the bottom of our unit shape here back to the original size. So if we go up, the size of our image doubles and the number of channels halves. So with fastai, we have a special unit learner that we can pass in the configuration, which is unit config, where we can declare a few things like floor or floor final to avoid a checkerboard, self-attention, which is a self-attention layer, Y range, which is last activations go through a sigmoid for rescaling, last cross connections with direct model input, bottle, which is bottleneck or not on that cross, and we can also adjust the activation function and normalization type. Okay, so let's make our unit learner that will use self-attention layers and mesh as an activation function. So as you can see here in our unit config, we set our self-attention attribute to be equal to true, and we are going to use mesh as our activation function. And then we are going to use ranger as our optimizer function. So here we set our OPT variable to be equal to ranger. And here we are going to build our unit learner. So we pass it our data loaders, our ResNet34 architecture, and our accuracy functions that we declared earlier, along with our configurations and our optimization functions that we declared. And now we can do learn.summary, and as you can see here is the results. Okay, and then we are going to find a learning rate. So we are going to use LR underscore find method, and we are going to use 10 to the negative 3 as our learning rate. So here we declare our LR variable to be equal to 10 to the power negative 3. And with our new optimizer, which is our ranger, we will also want to use a different fit function. So we are going to use a fit flat cosine. So here we use it, pass the number of epochs, which is 10, along with our learning rate. And here is the results. Okay, so let's save our model and show the results. So here's our target, and here's our predictions. And as you can see, our model in just 10 epochs did very, very well. Okay, so let's unfreeze our model and follow the rule of thumb, which is when you unfreeze your model, you divide your learning rate by 4 in the tail end and 400 for the high end. And here's our new learning rate. Then we are going to unfreeze our model, and we train it by using our new learning rate with 12 epochs. Then we are going to save our model. And here's our results, and if we look at our results, there is a little bit more improvement now compared to before. Okay, so let's go with the final part, which is inference. So let's take a look at how to do inference with test data loaders. So test data loaders is how you can do a batch predictions on a whole bunch of images at once using the GPU. So to do this, we pass a list of file names, which is our first 5 images, to learn.dls.testdl. And here we show batch to make sure that everything works. And here's our images. Okay, so now let's get the prediction. So here we call learn.getBreads and pass it our data loaders. And if we look at here, we have a 5 by 32 by 360 by 480. So this 5 here is referred to the number of images that we have. So we have 5 images. And this 32 is referred to the length of our codes. So we have 32 codes. Okay, so now let's go ahead and grab the first image. So it exists at the first prediction layer. And if we print its shape, it's 32 by 360 by 480. So now let's take the argmax of our values. So here we call argmax function and pass it the dimension of 0. So this function returns the indices of the maximum value in a tensor along the first dimension. And now let's show it, and as you can see, it's look like a mask. Okay, so what to do from here? We need to save it away, so we can do this by using one of 2 ways. First, we can save it as a numpy array, and or we can save it as a tensor. So here we converted to numpy array. And this conversion here to rescale everything to 255, which is what normal images are expected to be one channel images. Then we make an image from array after rescaling. And as you can see now, we have it in a grayscale. And now we can save it. And another way to do this, we can save it as a tensor. So we can save this tensor away as .pt. And to load it back, we can call torch.load. And as you can see here that we have the exact same result that we saw before. Okay, so that's it for today's video. Hope you enjoyed.